Day 0, if you want to call it something. Day 0. Calculus 12 AP and the integral as the net change and as an accumulator. So what does the integral of the velocity function give you? Well, yeah, it gives you the area under the velocity. Okay, so yes, it gives you the, okay, so what does that tell you though? So time, velocity, and you got some velocity curve that looks like that, and then yes, it gives you the area under that curve, but what does it do for you? When you find the area under a velocity curve, it tells you distance. Like if you drive 3 meters per second, for 6 seconds, or your velocity at the end, so you can, let's find the area of that triangle. It's going to be a half times base times height. 6 times 3 is 18, half 18 is 9. Now, when you drive 3 meters per second, 6 seconds, that means you're starting at 0, blah, 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 blah. Physics people, VF plus VI. You're 9 meters from your starting point, are you not? Physics 11 people. How do you find displacement? Using initial velocity and final velocity. Oh, wow. Mr. Abraham, it's time for a phone call. VF plus VI or divided by 2 times T. Well, guess what? 6 plus 0 divided by 2 times 3. Guess what you get? You get 9. So, physics people, math people, the integral of velocity is position. Because we've taken the derivative of position to get velocity, right? So what does the integral between 0 and 3 tell you? It tells you s of 3 minus s of 0. It tells you how far you've traveled in 3 seconds. Or it tells you your displacement in 3 seconds. I think that might be a better way of saying it. Because we could have negative things here, right? It tells you your displacement. Right? So, given the graph of the velocity particle at moving on the x-axis, the particle starts when x equals 2, at x equals 2 when t equals 0. Find the net distance traveled by the particle during the trip. Well, all I'm really asking you to do is to find this area plus this area, plus, minus, plus that area. So, what's the area of region 1? Region 1 is a triangle. Base times height divided by 2. 2 times 3, half of 2 times 3. 3? Yeah? And then this part here is a trapezoid. Area 2. Area 2 is a half. Base 1 is 3 to 6, 3. Base 2 is 2 to 7, 5, times the height, 3. Half of 8 is 4, 4 times 3 is 12. Area 3. Area 3 is another triangle, a base of 3 and a height of 3. I don't know why I'm using brackets now, but anyways, 3 times 3 is 9, half of 9 is 4.5. So find the net distance traveled by the particle during the trip. What am I going to do? That's 4.5 minus 12 equals 7.5 minus 12 is 4.5 negative. So you could say 4.5 units to the left. If I ask you where you are, you would say 4.5 units to the left of where you started. Yeah. Find where the part. Oh, I did that. Well, but we got to be careful how we say this. 4.5 units left of where you started. Well, you started at x equals 2. So where are you now? Yeah, you're at the point x equals negative 2.5. Find the total distance traveled by the particle. Well, you went 3 units this way, you went 12 units this way, and then you went 4.5 units that way. How far did you walk? $19.5 meters if we're using meters. Units. 19.5 units. I don't know if the units are anything on here. What? Craig. It just says it started at 2 in the sentence, in the information. Yeah. It's kind of hidden, right? It's on the beginning of the next line, and if you're not reading carefully, you're just going to miss that. You're going to say negative 4.5, right? So be careful, watch out, right? Well, I mean, we could take this information. I mean, technically, we could take this information and draw a position time kind of sketch where we're starting at 2, and then we go 3 units right, so we're now over to 5, and then we're 12 units left, so now we're over here at negative 7, and then we're 4.5 units right, so we're now at negative 2.5. Well, yeah, it's velocity versus, that's why it's coming up, because it's positive velocity and negative velocity, right? It's really hard to draw, like a position time graph for this picture is going to, well, I guess position time, we could pull it up and do the position as the distance above the axis. But it would look really hard to see this graph, right? Right? Because it's all on the same line. We could make a little movie that did it, but in terms of graphing it, it's much more challenging. Okay, velocity of a particle is given by this formula. If the particle is moving horizontally along the x-axis for t equals 0 to 5. Okay, so throw this in your graphic calculator and draw the graph of the velocity function and describe the motion of the particle. So I want to know when the particle is stopped, I want to know when the particle is moving left, and I want to know when the particle is moving right. So throw it in your calculator and draw it. And tell me everything you know about this. So yes, I know this is a review from chapter 4. But you guys are big kids. So window 0, enter make my window bigger. Okay, so I guess we should find out when the particle is moving left, when it's moving right, and when it's stopped. So I want to know that coordinate. So I'm lazy, I don't want to do it algebraically. Second trace, 0, 1, enter, 2, enter, 1.5. You guys knew you could do that without arrows, hey? When it says left bound, you could just use the tick marks and say, ah, it's about here. 1.254. Yes? 1.254, 547. So, velocity is 0 at t equals 1.254 5447. So when is it moving left? Between where and where? Yeah. When is it moving right? 1.254 5447, comma 5. B. Because you're stopped at 1.25. You're not moving right yet. Or left. Okay, so suppose the initial position of the particle is s is 0 equals 9. What's the particle's position at? So what I'm asking you to do is to do this. The integral of t squared minus 8 over t plus 1 squared. So this is going to take a little bit, well, I don't want to say a little bit of grinding, but it's going to take some grinding, right? So, I would recommend doing this. Splitting the integral into two parts. One part which is easy to do, and one part which is easy to do. Together they're not as easy to do. Know what I mean? So, antiderivative of t squared is t cubed over 3. Can you look at the antiderivative of 1 over t plus 1 and tell me the answer? Yeah, neither can I. Well, I can, but I'm not going to do it. That's intimidating if I start doing that. U equals t plus 1. So du over dt equals 1. What is it going to be? Negative 1 over t plus 1. Just up to the first. Up, just yeah, that's it. So you do that, and then you guys are telling me the answer. But I didn't want to skip any steps, so we will write it as, and then the antiderivative is, so you got u to the negative 1 divided by negative 1, right? So negative 8 u to the negative 1 over negative 1. Now, we can come all the way back up here. I don't know. I might have some room left. No, I don't. I'm going to write it like this. S of t equals t cubed over 3 plus 8 over u. Well, what's u? T plus c. Good call. Don't forget it. It's important here. It's not chapter 5. Sometimes you need them, right? Yeah, it will here, because if you look at the very beginning part of information, what does the very beginning part of the information tell you? It tells you S of 0 equals 9. So it tells you C, just not in the way you want it to. So S of 0 is 9. So 9 equals 0 plus 8 over 0 plus 1. I guess it's 0 cubed over 3. And then 8 over 0 plus 1 plus C. So it turns out C is 1. Now we can answer all the questions. But notice all the legwork that has to happen first. Okay, so what's the first question? So you just put t equals 1 in the formula now. S of 1 equals 1 cubed over 1 plus 8 over 1 plus 1 plus 1. So, no, like that. So it's 1/3 plus 8 over 2, 4 plus 1. So 5 1/3. Or 15 16/3 if you want. S of 5. 5 cubed over 3 plus 8 over 5 plus 1 plus 1. 125 over 3 plus 8 over 6 plus 1. Yucky. Whatever that is. 125 over 3 is 125 over 3. Well, I guess you could write it as 40. Okay, is that the final answer? 132 over 3, or some mixed number if you want. Find the net distance traveled by the particle in the first 5 seconds. Well, the particle, it's telling you S of 0 equals 9. And we tell you S of 5 is 132 over 3. Because what you're doing is you're integrating the velocity function from 0 to 5. So t squared, is it minus 8? I can't even remember. You're integrating that, right? But what you're really doing is doing the antiderivative velocity is position, right? So you're doing S of t between 0 and 5, and you've already done that work. It's 132 over 3 minus 9. Is it tying things together, though? That's what I'm really trying to hope. That's actually why I delayed this so late, is I'm trying to tie things together. Say, hey, look, this is just the same thing. We're just looking at it, instead of from a derivative perspective, we're looking at it from an antiderivative perspective. It does look more like Chapter 5. Yes. And it should have a feeling of Chapter 4. Just, hey, look, all we're doing is undoing Chapter 4 here. Right? Chapter 4 was all to take the derivative to do things. Here we're telling you the derivative and asking you to go backwards to undo things. Right? Okay. Find the total distance traveled by the particle in the first 5 seconds. Okay, this is going to take a little bit. This is going to take a little bit of calculator work because I'm lazy. So what I want you to do is I want you to find this area, please. Use your calculator for that area. That's the other reason why I made that number when I wrote down that t so accurately, 2.545474, that number. Good work, whoever that was. 1.2545447. And I need decimal point in there. So negative 3.793443. I'll write that down somewhere. Negative 3.79 what? 3443. Okay, so we got that part done, and now the part. Next question while I'm doing this is, do I really need to do this calculation? I'm smiling evilly. 38.793443. 38.793443. Can I get this red area without actually, that top area without actually doing that calculation? Take a look at your net answer. Take a look at how that 3.79 might affect that net answer. Yeah. No. Well, it's just added on, right? Like, this net answer here. Anyways, so find the total distance. What am I going to do to find the total distance? 38.79. There you go. Plus the 3.7. What? No, this isn't taking into consideration where you started. All it's doing is finding how far you traveled. I can't, that area calculation will not tell you where you started. It will only tell you how far you are from your starting spot. Okay. So add those together and what do you get? 38, 30, 41, 42 point 6725. Okay, keep on going. Car with moving an initial velocity at 5 meters per second accelerates at a rate of 2.4 hour for the first 8 seconds. How fast is the car going when the 8 seconds are up? Well, what it's saying is, here we're going to graph it. T, A of T, no, B of T, no, we'll put A of T here. It's going to look like this. Right? Okay, so what you're doing is you're doing the antiderivative without actually recognizing your, no, it's 2.4, no. Yeah, it's 2. If it was just 2.4, it would just be 2.4 times 5. Sorry, 2.4 times 8 plus 5, but it's, because what you just did was the antiderivative, right? So we know the acceleration function, A of t equals 2.4t. To go backwards, to find velocity, what do? Take the antiderivative, right? Yeah. So you get 2.4t squared over 2 plus c. How do you find out C? You put 0 in for T and you put 5 in for V. So 5 equals 2.40 squared over 2 C. C is 5. So V of 8 is going to be 2.4 times 8 squared over 2 plus 5. I'm surprised you guys are okay with the 2.4 over 2. I would have changed to the 1.2, but is that okay? Yeah? No? Yeah? Okay. How far did the car travel? Mr. Epp, take the velocity in, integrate it now. So, integrate V of t. Integrate 1.2 t squared plus 5 dt. While the antiderivative velocity is position. 1.t cubed over 3 plus 5t plus c. And we want to know how long we did it for 8 seconds. Well, 0 to 8. 0 to 8. Put in 8, put in 0, subtract your answers, and you know how far you traveled. Is this a nice review of chapter 7? Or sorry, chapter 5? Mr. Epp, you are evil. Okay, 0.4 times 8 cubed plus 5 times 8 plus c minus 0 plus 0 plus c plus 0 plus c. So you end up with some number. From 1970 to 1980, the rate of potato consumption in a particular country, this is exciting, was C of t equals 2.2 plus 1.1 to the t millions of bushels per year, where t being years since the beginning of 1970. How many bushels were consumed from the beginning of 1970-73? In 1972 to the end of 1973. That would be the beginning of 1974. Now, did I do anything about antiderivatives of 1.1 to the power of t? No, so maybe we should graph this. Yes. Let's do a little graphing. Little graphing music for all the fans out there. Graphing. Who cares what it looks like? Second trace 7 to enter 4 enter. Monsieur Epp, we sold, we consumed 7.066031 million bushels. 7.0 what? 66 million bushels. A whole lot of potatoes. Something like that, million bushels. That wasn't so bad. Yeah. Okay, last one. Yay! Woohoo! Sit back. No, we got to do one more little thing of chapter 4. We're going to do that on Friday. I know, it's the sense of... Oh. So, a pump connected to a generator operates at a varying rate depending on the power being drawn from the generator to operate the other machinery. The rate, gallons per minute, at which the pump operates is recorded in 5 minutes per 1 hour. In the shown below, how many gallons during an hour? Well, this looks familiar. Chapter 5, nice review of 5. How do you suppose we determine the total amount under a curve when we're given a table of values? Riemann sums. You guys are awesome. What are we going to use? We're going to use left endpoints, right endpoints, midpoints, trapezoids. Not trapezoids. We're going to cry. What? Right endpoints? How many strips? One. I don't know how many are here. 6, 7, 8, 9, 10, 13. I was just, look, let's just do this. So 1. No, let's do groups. Yeah, can we get away with groups of 3? I don't know. 1. No, you got to be careful how you did it. 2, you got to overlap them. 3, 4, 5, 6. You got to overlap. I don't know. Are we doing traps? Are we doing endpoints? What are we doing? Oh, traps aren't so bad when you're doing. So we're going to do half of 58 plus 65 times 10 plus a half 65 plus 58 times 10. No, it's the width of the bar, dude. 5, 10, 15, 0, 5, 10, sorry. A half 58 plus 55 times 10. A half. I'm getting lost. 55, 59. And then 59 and 60. And 60 and 63. How's that? And then you reach for your, no, we'll just stop. Then you reach for your calculator, you type it in. Yeah? Other questions that I've seen asked, or I'm starting to look at the AP exams to get some feelings for, like, they'll give you a list of this data and then they'll ask you a gazillion questions about it. So one of the questions is how much water flow will be pumped. And then they'll say also, write an integral that represents what we just did, which is easy, right? So it'd be the integral from 0 to 60 of, I don't know, what letter are we going to represent? I don't know, R of t, right? dt. And that'll tell us how much water has been pumped out. Other questions that could be asked are, when is the pumping increasing? When is it decreasing? So you have to look at the table and see where the number is getting larger. So from 0 to 10, it's getting larger. And then from 10 to, so from 15 down to 35, you would say it's decreasing. And then from 55 up to 50, up to 60, you would say it's increasing. Yeah? So you're going to get asked questions that are going to take you back to chapter 3 and 4 as well. Another question would be something about the mean value theorem. When does the rate actually go horizontal? Is there any point C? And then you can look and you can go, well, Mr. At there are lots of points where it's 0. Somewhere between 35 and 30. 55 minus 55 is 0. So there's some point C in that interval between 30 and 35 where it's going horizontal because those two y values match. Right? So be prepared, all those AP exam writers. Be prepared for questions that will ask you to do multiple things with one set of data. That's what makes this test hard. It's the willingness to do multiple things with a piece of information. Okay? That's it. Yay.